Hey, sports fans. I hope we're ready for some more calculus. This is a topic recently that my students took quite a liking to. Hey there and welcome. This is Planet Numeracy. I'm Mark Noldy, your personal math coach. Let's talk about the integration technique known as substitution. Okay, so here is how the using substitution comes into play. If you saw a problem like this, antiderivative of 2x times the quantity x plus 5 quantity squared, we could do this. We would just have to FOIL this out and, x plus 5 times x plus 5, and then go through and distribute the 2x, and then we could take the antiderivative term by term. But what happens when, say, this is x to the 20th power? So that would be, could I multiply this x plus 5 times itself 20 times? I could. Take a long time, and then I could distribute the 2x on that long polynomial. But it would take a long time. So there's an easier way, and that easier way is called the integration by substitution. So essentially, integration by substitution is sort of the reverse of the chain rule. So if you remember the chain rule, the integration by parts looks a lot like the chain rule. And I'll show you what I mean on the next page. So suppose I took the derivative of function f of g of x. So we know from the chain rule that this is equal to the derivative of the outside, and don't do anything to the inside yet, but then the last step is to multiply by the derivative of the inside. And that is where the chain rule starts. That is the chain rule. So what we do to get our integration by substitution down is we say, all right, what happens if I take the integral of both sides of this equation? Which I can do, right? I can take the integral on both sides. So the integral of the derivative is just the function, right? So f of g of x. And on this side, I would just have f prime g of x times g prime of x. And of course, I forgot my dx here, didn't I? Probably need one of those up here as well. So when I take the antiderivative of a composite function that's multiplied by the derivative of what's inside the composite function, I go right back to the function of what I was looking for. So let's go back and consider the function. Let's see, what did we have? 2x times x plus 5 to the 20th. So what you'll notice here is I have a function that has sort of an inside, a chain, being raised to the 20th, and the derivative of this function, which goes over here, is 2x. It is 2x because I forgot a 2. So this inside derivative of the inside is the 2x. So where substitution comes from is we say to ourselves, all right, we're going to substitute the variables. So we would say let u equals, in this case, x squared plus 5. So this is my u. That would make the derivative of u, du dx, it would turn it into just a 2x. And this would usually get written as du equals 2x dx. We're just, moving the dx over. So, go back to substituting here. we're going to say, I have u, I've already marked that here, and I have a du. So du is equal to 2x dx. And here's a 2x, and here's a dx. So I can rewrite this now. I could say, well, that is u to the 20th power du. And the du, again, is taking the place of this 2x dx. And u is just taking the place of x squared plus 5. So can we take the antiderivative of u to the 20th? Of course we can. So we would say, all right, that becomes u, let me go back to my white color here. That would become u to the 21st. And if I take my old coefficient and divide by my new exponent, I'd have 1 over 21. So that becomes 1 over 21 u to the 21 plus c. And we can check this. 21 times 1 over 21 is the 1, and u is still the same as u. But notice we started in x, so we want to end in x. So I have to go back and resubstitute x squared plus 5 in place of the u. So my final step here would be to say this is equal to 1 over 21 times x squared plus 5 to the 21. And don't forget your constant, plus c. So again, we can check this. If you check this and did the chain rule here, you'd have 21 times 1 over 21 is 1. And then you would take x squared plus 25 to the 20th, which we have up here, and then times it by, multiply it by the derivative of the inside, which is 2x. So when we check this, take the derivative of this, we go back to where we started from. So that's the way to double check that. So this technique gets used quite a bit. Okay, there's a lot of other techniques of integration, but substitution will be used a whole heck of a lot from here on out. So let's go and look at another example. So here's another one. It's got a cosine with it, but it's antiderivative of 3x squared times cosine of x cubed dx. So typically speaking, whenever you see a multiplication, most of the time you will be looking at doing substitution. But what we have to do is decide what are we going to substitute. We need a u and a du. So we need to pick a u so that when we get a du, it becomes a piece of this puzzle here. So usually, if I have an x cubed, the derivative of x cubed happens to be 3x squared. So I would start with x cubed as being my u. So let's go and make that a u. So that would make du be 3x squared dx. And remember, this is the way we write this. I don't put the dx under here. I move it over to this side so that I can match it up with something over here in the expression I'm looking for. So I have a cosine of, well, this is my u, so I'm going to put u in here. And then du, that's 3x squared dx, and here I have a 3x squared dx. So that just becomes my du. So I'm taking the antiderivative of cosine of u du. So we know how to take the antiderivative of cosine. The antiderivative of cosine is, of course, sine. So I would have sine of u plus c. Now, remember we started with x's 3x squared and x cubed, and we change it to u's, and now we have to change it back. So wherever I see a u down here, I'm going to put an x cubed in for it. So let's do that as our final step. Sine of x cubed plus c. And the best way to check these, if you want to, is take the derivative of this. The derivative of sine of x cubed would be cosine of x cubed, which we see up here, times the derivative of the inside, which is 3x squared. So this does check out. So here's another example where we can go ahead and insert numbers if we need to. So I'm looking at x cubed plus 4, and if I take the x cubed and take its derivative, it's 3x squared. But all I have here is an x squared. Wouldn't it be nice if there's a 3 there? Can I put a 3 in there? And the answer is yep, you can. You can multiply by 3 so long as you divide by 3. So we accomplish that by multiplying the outside by 1/3. 1/3 of 3 is 1. So we haven't changed the value of this, but we've set it up so that we can take the derivative, undo that, do my substitution first. X cubed plus 4 has the derivative du 3x squared dx. So 3x squared dx. And let's see, I do have a 3x squared dx right here. And I have a u right here. It's just being raised to the half power. So I'm going to make my substitutions. Now, you have to remember a common mistake is to forget to bring this 1/3 along. So make sure we bring that along. And this just will become antiderivative of, I'm going to write it as u to the 1/2 du. So again, this is my u to the 1/2, that's the square root symbol, du. So the du is 3x squared dx, so it matches up with our substitutions. So now we can just go and take the antiderivative. So that gives me 1/3 times, let's see, 2/3, because this is going to go to u to the 3/2. So 1 divided by, let's see, 3/2 is 2/3, and check it, 3/2 times 2/3, that gives us the 1. So the last thing we have to do is add our constant of integration. So that would be plus c. So usually what we'll do is just multiply these two, but technically what's going on is you would be distributing that on the whole thing. So I'd have 2/9 u to the 3/2. But 1/3 of c is just a constant, another constant. So that's why a lot of times you will see people do this without sticking these parentheses in there, even though they're technically there. So that's the almost last step. What we have to do now is go back in and substitute what was my u, x cubed plus 4. So x cubed plus 4 to the 3/2 power plus c. And usually we leave those just like that. That's usually fine to leave those that way. All right. Those are indefinite integrals. There were no boundaries of integration. Let's look at one that has boundaries of integration. All right, so let's look at this one. So here I have boundaries of integration. My lower bound is 0, that's my A, and my upper bound is 2, that's my B. So I have some stuff going on here. I have a polynomial raised to a 6th, so I tried to make this such that nobody would try to expand this 6 times. So let's go ahead and see if we can do a u substitution. If I made this be u, x squared plus 2x plus 8, I'd have a du of 2x plus 2. Well, I almost have a 2x plus 2 here. In fact, if I multiplied that by 2, I'd have 2x plus 2. And the only penalty to pay there for that is to say I have to divide by 2 or multiply by 2 on the outside if that's what I'm indeed going to do. So let's go ahead and define our variables. I have, let's let u equal the long one, x squared plus 2x plus 8, which would make du be 2x plus 2 dx. So here's my 2x plus 2 when I distribute the 2, and here's my dx. So that takes care of this. Over here, I have u to the 6th power. So I'm going to rewrite that as u to the 6th power, and then I just have du. Then I'm taking the antiderivative of that and multiplying by a half. Now notice I did not put 0 and 2 here because 0 and 2 went with the x's. So I have to change these numbers from 0 and 2. And the way we do that is we say, well, what is x equal to? Well, here it's equal to 0. So in u's, I come back over here. What is 0 squared plus 2 times 0 plus 8? Well, that would make my lower bound be 8. And then come back and look at the 2. When x is 2, u would be, let's see, 2 squared is 4, plus 2 times 2 is another 4. So 8, and 8 plus 8 is 16. So that would make our upper bound of integration be 16. So now we have a much easier looking problem to take the antiderivative of. And in fact, we don't have to go back to x. We can integrate it using 8 and 16, and that'll save us a few steps of having to go back. So let's try this. U to the 7th. So old coefficient divided by the new exponent is 1/7. And when I check it, 7 times the 7th is 1, so that's good. Then I'm going to have, let's see, plus c. And usually at this point we're not going to put a c in here because we know that the c's will add off when I expand this. But I'll leave it in there just for this problem. So 1/2 times 1/7. Let's see, u starts at 16. So I'm going to have 16 to the 7th plus c minus, let's see, 1/7 to the, now I'm going to use the 8, 8 to the 7th plus c. And then, of course, the whole thing gets multiplied by a half. So when we go to expand this, I'm not going to expand this because I don't have a calculator with me, but I would have 16 to the 7th over 7. Let's see, then I would have plus c minus 1/2 times 1/7 times 8 to the 7th. And this minus, when it gets distributed on the c, becomes a minus c. So a lot of times I let my students not write the c in because they know it's going to add off in the end. So if you have a calculator, you can go ahead and simplify this. So I'd have, let's see, 16 to the 7th over 14 plus, no, minus 8 to the 7th over 14. And that would be my evaluation for what I started with up here. So stop the video for a second and see if you can get that. So here's one last one to look at. This uses substitution, but it throws a little bit of a wrinkle into it. We would ordinarily think that x plus 1 should be our u, but if I do that, what is my derivative going to be? Well, if u is x plus 1, that makes du just 1 dx, right? And I don't have a 1 here. So this is one thing that we can do. I can't do this if this is x squared or x cubed or any other exponent other than 1. But I can do it this way. I can say, well, I'm going to go ahead and let u equal x plus 1. So I'll have x plus 1 to the 1/2. And then my dx is my dx. But x, I'm going to write in terms of u. So that becomes what? X would equal u minus 1. So in place of this x, I would have u minus 1. And in place of this part, I would have u to the 1/2 du, and I'm taking the derivative of that. So this is an indefinite integral. It's just to show you how to do this technique right here. So now what we do is we distribute. So I'd have the antiderivative of u to the 3/2 minus u to the 1/2 du. And then I would go ahead and take the antiderivative. So that would give us 2/5 u to the 5/2 minus, let's see, 2/3 u to the 3/2 plus c. And this, we'll leave the c in because it's not a definite integral. There's no boundaries of integration. So we're just taking its antiderivative here. So let's go ahead and go resubstitute our u's. Resubstitute the x for the u's. So this would be x plus 1 raised to the 5/2 minus 2/3. U becomes x plus 1, and that's raised to the 3/2 and plus c. And again, we usually just, at this point in time, you've taken the antiderivative, so we just leave fractional exponents as fractional exponents in my class. It would be a pain. It would be an algebra problem after that if we wanted to write this with rationals or with radicals and then rationalize the denominator. It would be more of an algebra class at that point. So for that reason, we leave them, keep it this way here. So hopefully you got some value from that. If you have anything to add, please go ahead, comment down below, and we will see you in the next one. I hope you got some value from this. If so, hit the like button and subscribe. And don't forget, math is not a spectator sport. If you want to get good at math, you have to do math.